Here I'm going to use the Biot-Savart law to find the magnetic field due to a point charge. But in this problem, the radial vector is at an unusual angle. So the Biot-Savart law says magnetic field due to a point charge will be mu q v cross r hat over 4 pi r squared. All right, according to the coordinates given, the coordinates for P are 1, 0, 1. And we have our origin here. Let's go ahead and draw the coordinate system in this situation. All right, so this is going to be the positive x direction. Positive y is into that plane, and positive z is up. We can try to draw that on the picture itself. All right, that looks pretty good there. Now, in order to truly solve this problem, we're going to need to know the distance, the physical distance from the charge to the point where we're evaluating the field. And since we have a situation where we have a triangle created here, we can use Pythagorean theorem. So this is 1 meter by 1 meter there. So this is going to be radical 2 meters then. So I'll just write that down, that r is radical 2 meters. This is 1, that's 1, and this is radical 2, the distance from the charge to the point. All right, another thing we're going to need to know is the Q of our charge. So it's not just a proton here, it's actually a +2 microcoulomb charge. We'll need to know the speed of it, and that is 100 meters per second. The velocity is in the positive x direction, so that's positive I hat. Let's find the magnitude of the field at P. For that, we'll write B equals mu Q V, and then we can use sine of an angle. In this case, they said the angle here was phi, and that's going to be 45 degrees. Later, we can determine the direction using one of the right-hand rules. All right, so let's plug in. Okay, that's everything we need for the magnitude. Okay, I'm getting 7.1 times 10 to the minus 12 Teslas. Okay, now we want to use a right-hand rule to determine the direction of the field. One option is to point our thumb in the direction of the moving charge, or the current in this case. It can be thought of as a current. And then we would wrap our fingers in a curled fashion. Okay. The type of magnetic field lines we're getting here will be circles that look like this. Some of these are already drawn for us. And no matter where you are, if you think about this like a current carrying wire, the field lines will continue to be concentric circles. Okay, so this shows that the magnetic field will be out of that plane. Interestingly, according to the directions given here, positive y was into the plane, which means that the direction out of the plane will be negative y. And so that's what we're going to want here, is that the vector magnetic field at point P will be 7.1 times 10 to the minus 12 Teslas in the negative j direction, which is the negative y direction.